Hi everyone. Last time we talked about numerical differentiation. So today, let's talk about numerical integration. Numerical methods for integrations are very important because even simple functions may not have exact formula for their antiderivatives, which is the indefinite integrals. So even when an exact formula for the antiderivative does exist, it may be difficult to find. So we all know that for derivative, any functions, we can always find the derivative, no matter how complicated it is. It could be a chain rule, product rule, and quotient rule all combined together. However, for integration, right, we learned in Calc 2, there are a lot of functions. I would say most of the functions that we are not able to find the integrals for that. Even though we learned some techniques like U substitution, integration by parts, trig integrals, trig substitution, partial fractions. But those techniques can only help us to solve some kinds of integrals, but not all. Okay, so that's why this session, numerical integration, is so important to us. After we learn these concepts, then I would say our Calculus 2 about integration is complete. Okay, so we're gonna learn two rules. The first one is the trapezoid rule. Okay, the trapezoid rule approximates the curve by a straight line passing through the points. So here, let me draw a picture. Okay, so we have the function f, right? And we have 2 points, A and B. Well, then this guy is f of A, that guy is f of B, right? Okay, so how do we approximate it? We use a trapezoid. Okay, maybe I should use a different colors, more. How about use green? So we're gonna use this trapezoid to approximate the area. Okay, and do you still remember what is the trapezoid rule? So a trapezoid, if this is A, this is B, sorry, let me make it more general trapezoid. Okay, and this is H. Okay, so for a trapezoid, what is the area of a trapezoid? Well, actually what we do is we consider one more trapezoid and put it upside down. Now we get a parallelogram. And then this is A, this is B, right? What is the area of a parallelogram? Is base times height. So, but our trapezoid is half of this parallelogram, right? So that's why it's half of the base. The base is now A plus B. The height is H. So far, so good, everybody? So now, in our case, the base, we have f of A, and this is f of B. And what is the height? Well, the height is B minus A. So the area is then 1/2 B minus A times f of A plus f of B. Okay, so this is the formula of the trapezoid. So far, so good, everybody? Okay, now, if we divide the interval of integrations from A to B into 2 or more subintervals, and we can use the trapezoid rule on each subinterval to obtain the composite trapezoid rule. Okay, let me draw a picture again here. So, let me first use orange. And so this is A, this is B, this is F. Okay, let's cut it into 2 subinterval. Okay, so far so good. And we're gonna use this guy and this guy, 2 trapezoids to approximate. And we call A is like x0, and then this is x1, and B is like x2, right? Where here we have 2 subintervals. Okay, so what is the trapezoid of the first one? Well, here let H be, so let H be the step size or the difference between the 2 consecutive points. right? In this case, h is b minus a over 2 because the total length of this interval is b minus a, and here we divide it into 2 subintervals, so we divide it by 2. Okay, then the first trapezoid is height over 2 times, this is f of a, this is f of x1. Right? The second trapezoid is h over 2, and we have f of x1 plus f of b. Alright, so now you can see both of them has the factor h over 2. We can factor that out. And actually, h over 2, because h equals b minus a over 2, then h over 2 is just then b minus a over 4. And then inside, you can see we have f of a, but we have 2 copy of f of x1, and then we have 1 copy of f of b. What happens if we cut it into more subintervals? Let's say we cut it into n subintervals. Then a is like x0, x1, x2, dot dot dot. B is like xn. Okay, then we add the area of the trapezoid of each trapezoid, right? Okay, and then you can see the h. What is the h now? So in this case, h equals b minus. Let me write here. H equals b minus a n divided by n, because we divide it into n subintervals. Right? And so we factor h over 2, then that becomes b minus a over 2n. And you can see when we add the insides, f of a, we get 1 copy. F of b, we get 1 copy. All the other interior points, we get 2 copies. Can you see? So the endpoints a and b, f of a and f of b, we only get 1 copy. And all the interior points, xi's, we get 2 copies. So that is the composite trapezoid rule. So far, so good, everybody? Alright, let's do some example. Okay, example, let's use purple. Okay. So consider the integral, definite integral from 1 to 2 of 1 over x dx. First, let's compute the exact value of the integral. B, approximate the integral using the composite trapezoid rule with n equals to 4 subinterval. What is the absolute error of this approximation? Okay. So keep in mind, even though this integral we're able to integrate, but for many other integrals that we are not able to integrate, we can still use the trapezoid rule. And here we want to use the trapezoid rule because we want to show you like how accurate these answers are. Okay, so A, compute the exact value. So the integral of 1 over x is ln of absolute value of x, evaluated from 1 to 2. So that means we plug in 2 first, minus we plug in 1. But ln of 1 is just 0. So the answer is ln of 2. Okay, and when we compute the composite trapezoid rule, we're going to use this formula. Okay, n equals 4. So let me write down the formula. Dx is approximately equals b minus a over 2n. And then we have the first point, and then the interior points, we have 2 copies. And the last point, we have 1 copy. Okay, and here n equals 4. What is A? A is 1, B is 2. So our integral is approximately equals B is 2 minus A is 1, 2, and n is 4. So far so good. And also let's draw the picture. So A is 1, B is 2. And we want to separate into 4 subintervals. What's the midpoint between 1 and 2? 1.5. What's the midpoint between 1 and 1.5? 1.25, and this is 1.75. So those are the points, right? These guys, 1 and 2, they are the endpoints, so we have 1 copy. But all of the interior points, we have 2 copies. So 2 copy of f of 1.25, 2 copy of f of 1.5, and 2 copy f of 1.75. And at the end, 1 copy of f of 2. So far, so good, everybody? Alright, let's continue. Well, 2 minus 1 is just 1, so 1 over 2 times 4 is 8. F of 1, well, what is f? F is 1 over x, so we have 1 over 1, and then f of 1.25 is 1 over 1.25, and 1 over 1.5, 1 over 1.75, and 2. Okay, so let's plot this in our calculator. Oh, by the way, because we want to compare, it's better to plot ln of 2 inside our calculator to get the decimals. Then we can compare them. Okay, so calculator, ln of 2 equals 0.6931471806. So 0.6931471806, right? Okay, yes. And then next, we're gonna calculate 1 over 8. And then we times 1 over 1 is 1, plus 2 over 1.25, and then, oops, see? Okay, sometimes you have to check what you type, okay, because you don't want to miss something. Even though sometimes we think we press the button, but if it does not show up in the calculator, then we have to type it again. Okay, at the end we have plus 1 over 2. See? I realized I have a mistake. It's 1 over x. When we plug in 2, that is 1 over 2. Okay, so gotta double check our answer. 1 divided by 2. And you know what? At the end, you should get some answer that is close to the true value. If it's way too, it's really off the answer, then we know there might be a mistake. Then we can go back and check our work. So our answer is 0.6970238095. 0.69702380 and then what? 095. Okay, you can see it is so close, right? There are like it's 0.69 something. And if we divide it into more subintervals, the answer will be more accurate. And let's calculate the absolute error, right? So absolute error equals the absolute value of the difference between them. And I just use the bigger number minus the smaller number because its absolute value doesn't matter, right? We just want our answer to be positive. So you can use your true value minus the approximated value, or you can use the approximated value minus the true value. Okay, so let's see. We have this number minus the previous number. Okay, so 0.00387662890. 00387 and then what? 66289. 66289. Okay, that is the absolute error. So far, so good, everybody. Okay, so that is the trapezoid rule and composite trapezoid rule, where we divide the interval into subintervals and we use trapezoid to approximate the area. Okay, next we're gonna introduce the Simpson's rule. Okay, so Simpson's rules, we approximate the function to be integrated by a quadratic polynomial, leads to the basic Simpson's rule. So instead of using a trapezoid, we can approximate by a quadratic polynomial. Okay, the approximation integral is given by. So let me draw the picture here. Okay, so here, let's say this is A, this is B, and in order to get a quadratic polynomial to approximate it, we know 2-point fix a line, 3-point fix a quadratic polynomial. Okay, so a quadratic function, which means we need 3 points. So we consider the midpoints A plus B over 2. Okay, so if this is the function f, we're gonna use a quadratic function that passes through those 3 points to approximate it, and we compute the area here. And the formula of this area is b minus a over 6 f of a plus 4 copy f of the midpoint plus f of b. Okay, so the middle guy here is 4 copy. We are not gonna go over why this formula is true, okay? But if you're interested, please come to ask me. I'm very happy to go over with you. Okay, applying the same idea of subdivisions of intervals to the Simpson's rule and required n to be even. Okay, that will give us the composite Simpson's rule. So let's say if n equals 4. Okay, if n equals 4, let me draw the picture here. So a, b, and n equals 4. So here this is x0, x1, x2, x3, b is x4. Okay, so this is, so it's like we cut it into 2 pieces, and each piece we have a quadratic polynomial to approximate it. So at this point, and this point, so it will give us a quadratic polynomial. This point, and this point, it will give us a quadratic polynomial. Okay, and for this piece, we use the formula h over 3. Okay, so by the way, in our previous example, h between the step size, the h is b minus a over 2, right? So this b minus a over 6 is actually h over 3. Okay, now in general, our h, see, h is like we have the interval b has length b minus a, and we divide it into 4 subinterval. So h is b minus a over 6. And now the formula for the area under this quadratic polynomial is h over 3 f of a plus f of x1 plus f of x2. Okay? And then the second one, we have h over 3 f of x2 plus f4 copy of f of x3 and f of b. Okay, we can factor out h over 3, and then you can see what happened here. We get f of a, f of b. So the endpoint, we have 1 copy. And then the interior points, we have 4, 2, 4, 2, 4, 2, 4. So 4 and 2 alternates, but you always start with 4 and you end at 4. That's always the case. So far, so good, everybody? Okay. So in general, n must be an even number. So for Simpson's rule, when I asked you to use Simpson's rule, and the n must be even. Okay, so let's draw a picture here. So here we have let's say A is here, B is here, and we're gonna divide it into n. So interval, that's x0, x1, x2, dot dot dot. This is xn, right? So it must be even because we need 3 points to generate a quadratic polynomial. Okay, so it must be even. So then the formula is h over 3, and h is b minus a over n, and then we have f of a, and at the end we have f of b, and the middle, the interior points, we have 4, 2, 4, 2, 4, 2, 4, 2, 4. They alternate, but you start with 4 and you end with 4. Okay, so that is the Simpsons method. Keep those in mind. By the way, the formula will be given in the exams. Okay, but they're easy to memorize, right? Okay, all right. So we have the same interval, okay? And let's use the Simpsons rule with n equals 4. So n is still 4. This is a good example because after we compute it, you can compare the both method, trapezoid rule and the Simpsons rule. Okay, so let's see. But let's make a guess. Which one will be closer? Think about it, the trapezoid rule, we only use the straight line to approximate it, right? The secant line to approximate it. But however, the Simpsons rule, we use quadratic polynomial to approximate it. So if we increase the order, and the approximation will be closer, right? Do you remember the Taylor polynomials approximation? If we increase the order of the Taylor polynomial, the approximation will be closer. Okay, so here and we're just gonna use this formula. Let me use the purple. Okay. All right. So here, what is A? A is 1. Oops. B is 2. H is, so n is 4. Then H equals B minus A over n, which is 2 minus 1 over 4. Oh, that's 1 over 4, right? Then let's see. We have the interval 1 and 2. We divide it into 4. And this is 1.5. This is 1.25. This is 1.75. We have the same points as before, right? And so I is approximately h over 3. So 1 over 4 over 3. And then we have f of 1 copy. And then the interior points, we have the coefficients is 4, 2, 4, 2, 4. They alternate, right? So 4 times f of 1.25. 2 times f of 1.5, 4 times f of 1.75, plus 2 is the endpoint, so f of 2. So far, so good, everybody? And here, you know, a over b over c over d is a over b times d over c. So 3 is like the c is actually in the denominator. So we get 4 times 3, that's 12. Okay, what is f of 1? Oh, that's 1 over 1. And 4 copy f of 1.25 is 1 over 1.25. 2 copy f of 1.5 is 1 over 1.5. 4 times 1 over 1.75. F of 2 is 1 over 2. So far, so good, everybody? Okay, let's plug this in our calculator. And your calculator, where are you? So actually, we can save some work. See what we get before. Copy it and paste it here. Just change some number. 1 over 4 times 3 is 12, right? And then you see the first one is still 1, and then next one the coefficient is 4. The second one the same. The last one coefficient is 4. See, we don't need to retype everything. It's almost the same thing. And the answer is 6 0.69325. 39683. So 0.69325. 39685. Is that right? 6383. Oh, it's not 5, it's 3. Okay, so far so good, everybody. Let's find the absolute error. Okay, what is the true value again? Let's see. What's the true value again? Let's go back. The true value is, ooh, yay, I can copy it. So let me copy it and paste right here. Okay, so I copy it and paste right here. I love to use the bigger number minus the smaller number. All right. So the bigger number is our approximation, that is 0.69. 693253963 minus that number. Okay, approximately equals to, let's see, calculator. All right, we're gonna use our approximation. This is our approximation. Subtract, what's the true value here? That's the true value, ln of 2, right? Okay. Oh, so we get 1.067877 times 10 to the minus 4. 1.067 and then what? 877 times 10 to the minus 4. And what does that mean? Well, it's 0.000106787. And you can compare with the last approximation. The last approximation is 0.003. You can see the Simpson's method is actually more accurate than the trapezoid method. So far so good, everybody? Yeah, and it makes sense. It agrees with our guess, right? We're using the quadratic polynomial to approximate instead of a line. Then, of course, it should be more accurate. Okay, so those are the trapezoid rule and the Simpson's rule. Let's do more example. Okay, so the following tables gives the velocity of an object t minutes after motions began. Use Simpson's rule to approximate the total distance traveled during the interval from 0 to 6. Okay, so far so good, everybody. So here we have we divide it into 6 subintervals, right? So here n equals 6, and then what's h? H is b minus a over n. B is 6, A is 0 over 6. You can see the step size is 1. And actually, yeah, it is. 0 and 1, the difference is 1. Okay, so the total distance by the Simpson's rule, that equals h over 3. And here, what are the points? Well, here we have 6 points, right? The first point, 1 copy. The last point, 1 copy. And the interior points, we have the coefficient is 4, 2, 4, 2, 4, 2, 4, 2. Alternates. So 4, 2, oops. This is f of 2, and then 4, f of 3, 2, f of 4, and oh, I need more space. Okay, and 4, f of 5. So far, so good, everybody? Okay, you see? Check the coefficient again. 4, 2, 4, 2, 4. Okay. Alright, so let's continue. H is 1. F of 0 is 0. and f of 1 is 1.3. F of 2 is 2.4. And then f of 3 is 4.5. F of 4 is 6.7. F of 5 is 3.8. F of 6 is 5.2. So far, so good, everybody. So let's plug this in our calculator. Okay, calculator. So let's see. Here we have 1 over 3 and then times 0, 0. 4 times 1.3 plus 2 times 2.4. Oops. Point. Plus 4 times 4.5 plus 2 times 6.7 plus 4 times 3.8 plus 5.2. Close. Enter. See, the answer is 20.6. Okay, so that is the approximation of the total distance traveled during this time from 0 to 6. So far, so good, everybody? Okay. Do you want to have more exercise? How about let's use the trapezoid rule to compute as well. Okay. So the trapezoid rule, let me write it down here. This is the Simpson's rule. For trapezoid rule, let me use a different color. Okay. Yeah, then we have more exercise. So trapezoid rule. Okay, so trapezoid rule, then the total distance is approximately equals to h over 2. Okay, and then we have f of 0, the last one f of 6, but all the middle ones, they are 2 copies. Oops. So far, so good, everybody? Yeah, you can compare the Simpsons rule, we have h over 3, then the trapezoid rule, we have h over 2. Okay? Alright, let's continue. So, h is 1, so we have 1/2. F of 0 is 0, and then 2 times 1.3, 2 times 2.4. And then we have 2 times 4.5, 2 times 6.7, 2 times 3.8, 5.2. Okay, so in order to calculate, we don't need to type everything again. We can just copy the last line and then change some number. Denominator change to 2, and then here 0, and then 2 times 1.3, 2 times 2.4, 2 times 4.5, 2 times 6.7, 2 times 3.8, and 5.2. See, the answer is 21.3. Okay? So now you can see the difference between trapezoid rule and the Simpsons rule. Alright, let's continue in video part B. See you soon. Bye.